Let's see here. All right. I will begin with a word of prayer. Let us begin. Dear Father, we thank you for this day. I thank you for the students. Just ask you to bless this class today, Lord. In your name I pray. Amen. Okay, so at the end of class, remind me to give you your no Dylan curses. Got a bunch of Dylan stuff. I have some old homeworks, and I also have the take-home part of the test graded. All right, so we are now in section 10.5, and let me begin with a definition. And so this is basically what's an analytic function. So let's begin with a definition. A function f, let's say from, I don't know, I guess from U to the complexes is analytic on dr of z naught, which is what? This is the disk z in the complex, such that the modulus of z minus z naught is less than or equal to r. In other words, the closed disk of radius r naught, radius r centered at z naught, right? If there exist coefficients a sub k in the complex numbers, such that f of z equals to the sum k equals 0 to infinity of a sub k times z minus z naught to the power k for all z in the disk of radius r centered at z naught. So there you go. That is the definition of analytic function. Now, one of my complaints about Gamelin's textbook is he defines analytic function to be what we've called complex differentiable. And I think this is better language because we have different ideas about a function on the complex numbers, right? We could talk about a function being complex differentiable. That would mean it's real differentiable and its differential is right complex linear, right? In other words, it satisfies f prime of z naught equals to what? F of z naught plus h minus f of z naught divided by h as h goes to 0. If that limit exists, then we say the derivative at that point is f prime of z naught, right? And if that difference quotient exists for every z naught in some open set, then the function said to be complex differentiable on that open set, right? If at each neighborhood of a point there exists a little open set on which the function's complex differentiable, then we said that the function's holomorphic on such a larger set, right? Holomorphic means that at each point, at least locally, there exists a little neighborhood, a little disk, open disk on which the function's complex differentiable. That's our meaning for holomorphic, yeah. What's that? I just didn't hear you.
When we're talking about analytic, we're talking about closed disks. Is that relevant?
Well, we can, at the moment I've just defined analytic for a closed disk, but I think we can extend that to mean functions analytic on some domain if at each point in the domain there exists a power series expansion.
Important whether we're working with domains versus regions.
Probably. Let me not get too far down that path right now. We will talk more about that as we go on. Maybe not today so much, but that family of ideas you want to look at right there is something we're going to go investigate. But at the moment, I just want to talk about analytic on a disk. All right. So let's do something that's not in the notes, but I allude to this calculation in the notes, but I don't actually do it. And so I might get into trouble right now, but let's try, okay? So what I want to do is I want to try to say, look at, suppose f is analytic, right? Consider f analytic near z naught. So I guess I need to give a meaning for that, right? What do I mean by that? I mean that there exists a little open disk near z naught on which f is analytic, right? I mean, okay, so, and that means, in particular, that we've got a power series for f, right? We can write a sub k times z minus z naught to the k power is equal to f of z, right? And I'm sorry, I really should write it the opposite order because in typical mathematical speaking, we think about the thing which is, it's more customary to write it that way. All right. All right, so f being analytic means I've got power series expansion for it. What would happen if we look at f of z divided by z minus z naught to, let's say, the m power? Well, let's say m plus 1 power. What would that give us? I think you can see that that would give us k equals 0 to infinity of what? A sub k z minus z naught to the what? So if I'm dividing by m plus 1, what does that give me? I mean, I subtract, right? We get what? K minus m minus 1? All right. I suppose this is for z not equal to z naught, right? And then, here's a fun thing. Why don't we try integrating? Let's try integrating this expression over a little circle of radius r naught, close to z naught, right? So then the integral over a little circle of radius r centered at z naught of f of z dz over z minus z naught to the m plus 1, yeah, would be equal to the integral over that circle of radius r centered at z naught of this series. And how would that work out? Well, let's just be, careless early 19th century mathematicians and just throw caution to the wind and commute the series and the integration as if we don't even have to think about it. All right, let's just flip them around. Ignore the fact that these are reciprocal powers. It's not even a series. It's a sum of reciprocal powers of z minus z naught, right? If k is less than m minus 1, there's some, kind of slightly, let's say, not quite kosher things going on here. It's definitely not a power series entirely. It's something else, isn't it? But these are constants. A sub k is constant. We can pull those outside the integration if we're willing, again, to be careless 19th century mathematicians for a second here. Z minus z naught to the k minus m minus 1 dz. But then the thing is, we've worked out that integration, right? We worked out the integral of z minus z naught to a power. Or I should have, the first day we talked about complex integration, or the second day at least. I might not have, but I should have. And if we did, what we would have found is what? Let me write it down here. The integral of z minus z naught to the, let's say, j power dz over a circle of radius r centered at z naught, it's just equal to 2 pi I times the Kronecker delta of j comma minus 1. Which is to say that that integral is 0, except in the case that the exponent is the minus 1 exponent. So that series of integrals is almost entirely 0, There's only one non-zero contribution from all of those things, namely the case that the exponent is -1, which is what? Right, so we only have to, this is equal to k minus m, -1 equals to -1, means what? K equals m, right? So this is 0 except for k equals to m, which leaves us with what? It leaves us 2 pi I a sub m. Well, I said m. Yeah, a sub m, right? Hey, what's that? What did we just derive? Through some sort of hocus pocus mathematics, but here it is. A sub m is equal to 1 over 2 pi I integral of f of z dz over z minus z naught to the m plus 1. But what else do we know about series? In fact, this we proved carefully last time. If you have a power series representation for a function, what is the significance of the kth coefficient? We showed that a sub m has the significance of being the mth derivative evaluated at z naught divided by m factorial. So if you put what I just wrote in brown together with what I just somewhat suspiciously derived, right, I would say heuristically derived, we have what? Cauchy's generalized integral formula. Yeah? Is that how I derived Cauchy's generalized integral formula? No, it's definitely not. Well, this is equal to m factorial over 2 pi I, the integral over the circle of radius r centered z naught, f of z dz over z minus z naught to the m plus 1. So there you go. That is Cauchy's generalized integral formula. And I think this helps you see why it's not surprising that early 19th century mathematicians found this result, right? If you find out, if you have this idea about doing a complex integral, and if you're investigating functions being, analytic, right? In other words, represented by a power series, you are aware that when you integrate a reciprocal function around a loop, you can get something non-zero sometimes, then this is a natural thing to look at, and it's not surprising that they would find this formula at all, really. But again, this is not quite legit for us, right? We have not developed theory, I don't think, which quite, I don't know, maybe we could make it legitimate. Do we have the theory to make this legitimate? I suppose we do, but I think to make this calculation legitimate, I just have to use the generalized Cauchy's integral formula, which then makes this a kind of circular derivation. So, yeah, there you go. Okay, now, the theorem I have in the notes is more careful than this. What's the theorem in the notes? So what I've just sketched for you is that analytic implies that you support Cauchy's generalized integral formula. So how about this? If a function's analytic, is it holomorphic? Does analytic imply holomorphic? What do you guys think? Does analytic imply holomorphic, and if so, why? We proved last time that if you have a power series, right, then it is what? It's normally convergent on its disk of convergence, right? So if I've told you that this represents the function on that disk, that means we have, normal convergence of this power series, amongst other things. And this power series is what? It's this infinite series formed of power functions. Are power functions holomorphic? They are, right? So this is a uniformly convergent series of power functions, which by our theory that we've developed is what? The limit function here, which is f, is thus likewise holomorphic, right? So yes, analytic implies holomorphic by the theorems that we've discussed the past few classes. How about the other way around, though? Does holomorphic imply analytic? Right, that's the question. Does holomorphic imply analytic? And let's say on disk, you know, the answer is yes. Okay, and let me show you why. This is the theorem. Actually, if you don't mind, I think we have the I think you guys have the definition of analytic in mind now, right? I can erase that, I think, yeah? It's taking up 25% of my board space, so I think it's time for it to go. Yeah. Again, the question is, does holomorphic imply analytic? And theorem 10.5.2 says yes, and here's how. Suppose f is holomorphic, which we had the symbol for, by the way. Oh, stink. Z in the complexes. I don't have a symbol for the thing I was about to write, unfortunately, because I've used D for the closed disk, you know? So I'm kind of stuck. This is the open disk of radius rho. So suppose f is holomorphic on there. Then, this is the claim of the theorem, f of z is equal to the sum of a sub k times z minus z naught to the k equals 0 to infinity, for z minus z naught less than rho, where a sub k is, you guessed it, it's given by the kth derivative evaluated at z naught divided by k factorial. In other words, a sub k is given by the usual Taylor formula, right? And this power series has radius of convergence r, which is greater than or equal to rho. All right. Moreover, for any fixed r, 0 less than r less than rho, all right, we have that a sub k is also given by 1 over 2 pi I, the integral over the circle of radius r centered at w, centered at z naught. Should have brought my glasses. F of w over w minus z naught to the k plus 1 dw. And that's for k greater than or equal to 0. And finally, if the function f of z is bounded by m for z in the circle of radius r centered at z naught, then the size of the coefficient a sub k is less than or equal to m over r to the k. So this theorem has more than the answer to the question I posed, right? It says yes. If the function's holomorphic, it's analytic. More than that, it might be analytic on a larger disk than the one on which, if you give me that it's holomorphic on a disk of radius 2, it might well be that the radius of convergence of that actually goes out to radius 3 or something. I mean, it could be, all we know for sure is that if it's holomorphic on the disk of radius rho, it's definitely analytic on at least that closed subdisk. All right, and maybe more, maybe more. More than that, we can either think of the coefficients of the power series in terms of kth derivatives evaluated as z naught divided by k factorial, a la calculus 2, right? Or we can think of the kth coefficient of the power series as being related to the integral of the function divided by, the k plus 1th power function centered at z naught. And finally, as if that's not enough, if we have a bound for the function, we have a bound for the coefficients in a natural way. So yeah, it's pretty nice. Let's look at the proof of this. So I give you guys a choice. Do you want to see me prove it at 0 or prove it at z naught? What's that? I heard a z naught, I heard a 0. What's that? Z naught. All right, you guys make me work for my money. All right, here we go. Suppose we have z and c, and modulus of z minus z naught is less than r is less than rho. All right? And also, we have magnitude of w minus z naught equals to r. All right? Hence, if we look at the magnitude of z minus z naught divided by the magnitude of w minus z naught, we have what? That is less than what? Less than r over rho. Oh, excuse me. It's less than, r over r, right? Also known as 1. So this quotient is a real number less than 1. All right? Thus, here we go. If we look at f of w over w minus z, we get what? We get f of w over w minus z naught plus, or rather minus, z minus z naught. This is that trick we used last class, right? The same adding z naught in the middle trick. And then what? Then you got to use your imagination. If you use your imagination, you can see that we can factor f of w divided by w minus z naught. And that leaves me a big old fraction here, 1, and then 1 minus z naught over w minus z naught. And why would we do such a thing? Well, I guess my question, the leading question I'm trying to ask here, in the big brackets here, what can we say about that? Okay, but we could do better than that. We're looking at 1 over 1 minus something, and that something is magnitude less than 1. Yes, geometric series. So I can take this and make a geometric series out of it because it meets this condition. So this gives us that f of w over w minus z is equal to f of w over w minus z naught times the sum, let's see here, my choice, k equals 0 to infinity of, well, z minus z naught over w minus z naught to the k, right? But we can clean that up, right? Clean that up a bit. That could be rewritten as the sum k equals 0 to infinity of f of w times z minus z naught to the k power divided by w minus z naught to the, looks like k plus 1 power. Right. And we can do that for any z such that the condition above is met. Now what I say is I say following the same logic as the z naught equal to 0 case. So now you guys are making me, got to go back to my z equals 0 case. What was my logic there? I said, we're given the convergence of the above series is uniform for w minus z naught equals to r, right? This series converges uniformly given that condition, right? We know that the geometric series converges uniformly on its disk of convergence. It's fine. It's not your fault. It's a stupid adapter killing me. Oh, look. Now it's plugged in, actually. Hooray. It just unplugs itself without touch. Who cares? No one cares. No one cares. All right, go back into this. All right, so this geometric series converges uniformly when the condition of convergence is met. All right, we proved this previously. So, great. I say that allows us to expand Cauchy's integral formula into the integral of the series of holomorphic functions which converges uniformly. It follows we are free to apply theorem 10.3.9 to exchange the order of integration and infinite summation below. So what I'm going to do is I take this calculation right here and then I integrate it. Is the thing. I'm going to integrate that. Let's see here. There's a couple different things we're chasing down, right? What do we want to prove here? We want to prove, one of the things we want to prove is that the condition of holomorphic implies that there exists a series that represents it, right? And then the other thing is this formula for the coefficient. And maybe those are not disparate goals. I mean, those are the same goal, perhaps. Maybe the process of finding the formula for this will give us the existence of the power series which represents the function. Yeah? Let's see how that happens. So I want to integrate this, right? Well, here's what I wrote for the other case. I wrote f of z is 1 over 2 pi I. Actually, I'm doing too much work here. You guys tell me why this makes sense. 1 over 2 pi I integral over the sorry, I'm adapting it. Circle of radius r centered at z naught. And here we've got f of w over w minus z dw. What's this right here? What's that stuff? I thought it said 51. I was like, what? No! That would be horrible. That's just Cauchy's integral formula, right? We know that's true because why? We assume what? F is holomorphic, right? And this is a disk, which is a subdisk. I mean, this is the boundary of a subdisk of the disk on which we know it's holomorphic, right? So we can apply Cauchy's integral formula here. And then we trade this right here, right? Trade this for that, right? And then what do we have? What can we do then? Now, I said something like, ow, stink. I forgot my what? What is it? This is Cauchy's generalized. This is Cauchy's integral formula, which applies for what? Holomorphic functions, yeah? So that's not an easy result to come by, but we proved that. That's Cauchy's integral formula. We proved that like a while ago now.
No, I know the formula. I just don't see f of z anywhere before that, so I'm just confused where it's coming from.
Oh, I'm starting that. That's the new starting point. What I want to do, right, my goal is to show that f of z is equal to a series, right? That would show it's analytic.
Yes.
So my jumping off point is Cauchy's integral formula, which we know. Then what I'm going to do is I'm going to take the integrand and I'm going to use the geometric series to repackage it as a series. We're not done yet. See, ultimately this is going to lead to a formula that gives us that f is analytic where the coefficients are given by this integral. It's maybe 2 more lines than we have it. See, this is dw. Now, I didn't write the summation down yet because I'm trying to save myself some writing. The thing that's going in the series, what can you say about that function for the w, for the choice of w and z that's at play here? This is a what? I mean, there's no actual division by 0 here, right? We're on the circle of radius r. W is a point on that circle, right? Centered at z naught. So the expression in red right here, these functions are holomorphic, right? And we also know that they're uniformly convergent. They have uniform convergence. They're holomorphic. So I can exchange the order of integration and summation by our integration summation exchange theorem. I've met the conditions needed to pull the sum out here. All right? And that's pretty awesome because I probably could have been greedier, right? Can you tell me what else I could pull outside the integral? Let me put this a little bit further over here. So you say I could, oh, you say that the what? Now w I can't. W is the integration variable. I can't pull out things with w, but there's one thing here that's conspicuously, is that a word? I don't know if that's a word or not, but maybe suspiciously, that's the word. That's a word. This guy, this one doesn't belong in the neighborhood, right? We should kick him out. Let's see here. You know, he's not from around here. We should put him out here, right? It's a transient function. We stick him. No, wait a minute. No. That's not our politics. That's here. We do not do that. We welcome transient functions. See, now I'm going to have to edit this if I'm not careful. All right. Do you see why I can do that? Does that make sense? Ignoring my stupidity. Let's see here. All right. And why would we do that? Because then, what's this integral equal to? I mean, there's different ways to look at it. One way to look at it is, oh, cool, that integral exists, and we're done, because that's, bring the 2 pi I, and then just, this is, let me rewrite it one more step here. So this is the sum, k equals 0 to infinity, right, parentheses, 1 over 2 pi I, integral over the circle of radius r centered at z naught of f of w over w minus z naught to the k plus 1 dw, that integral, which exists, times z minus z naught to the k. Hey, what do you know? Call this a sub k. We just showed that f is analytic. And then there's different ways you can go from here. The one way you could go is say, okay, so now we have f is represented by a power series, so we know that the meaning of the coefficient is that what? We know that the kth coefficient of a power series is given by evaluation right? It's given by evaluation of the function, the kth derivative of the function at the center of the series divided by k factorial, right? Or I could use the generalized Cauchy's integral formula to convert that integral to this, whichever way you want to go. But certainly we have this, we've got that, and this bound is just the ML theorem applied in the current context to a circle of radius r. So that's it. So there's like a circle of ideas here, and basically once you get on the train track of this idea, if you get one of these things, you can kind of get the other if you're willing to make some sort of cheesy analytical sleights of hands, right? Like we did at the start of class. If you have the idea of functions analytic, you can kind of derive the Cauchy's generalized integral formula if you're willing to do some slightly heretical analysis. Yeah. All right. So that's a pretty big event in this course that we just proved. And there's a corollary to this, which is really going to be a major player in what follows from here on out. Corollary 10.5.3. It says the following. If we have f and g are, let's say, I'm going to state it slightly differently. Suppose that they're holomorphic on a disk of radius r centered at z naught. Then if the kth derivative of z naught is equal to the kth derivative of g at z naught for k greater than or equal to 0, then f of z is equal to g of z for all z in the disk of radius r. It's driving me nuts to not have a notation. What should we call, you guys, let's put an O for open, if you don't mind. Can we do that? O for open. So let's say d r o z naught will be what? This is going to be z in the complexes such that what? Modulus of z minus z naught is less than r. Without the O, I include equality for the r, okay? If you want to, you're like, I want more topology in my life. Okay, great. The interior of dr z naught is equal to d sub r upper 0 z naught in our current language. So like this is dr, here's z naught. This is dr z naught.
So are you saying
They're both shaded in. What's that?
for all k greater than or equal to 0 or for some k greater than or equal to 0?
In other words, if the derivatives match, the functions are identically equal. What's the proof? The proof is very simple. You take what? You take the functions, they're holomorphic, therefore they're analytic, which means we have power series representations for both, right? And the coefficients for both power series match order by order by order, so they have the same formula. So they're equal at any point.
Is this a real theorem as well?
Is this a real theorem as well? No, it is not, because there exist functions. Well, I don't know what holomorphic means in the reals. I mean, certainly not true for real differentiable. There are smooth functions which have matching derivatives at arbitrary order and yet are not the same function. Key example being, pick your favorite real analytic function that has 0 derivatives at 0, and take the smooth bump function that has zeros, all the derivatives being 0, and yet it's not analytic. I mean, there's, I'm talking about, there's this function that's super smooth, like at 0, it's got the kth derivative at 0 is equal to 0 for all k. And yet, you of course could take, can you guys think of a function, a real function that has all of its derivatives being 0 at 0 and is real analytic? What function is that? We will soon prove that's the 0 function. That's your only choice. Those are not equal, despite the fact that they have matching real derivatives of arbitrary order at 0. It goes back to the larger point that there exist real functions which are smooth but not analytic. There's no such thing as a function which is complex smooth but not complex analytic, because complex smooth or holomorphic implies analytic. That's what we proved today. Complex functions are really, really nice. Complex smooth even is kind of a silly term, because complex differentiable, one complex derivative implies infinitely many complex derivatives, right? Continuous differentiability loses meaning in complex analysis, because if we have one complex derivative which exists on an open set, we proved with Morera's theorem and Gorsaw's theorem, that arc of the course, we proved that the existence of the complex derivative on a domain implies that that derivative must exist continuously. Right? This result's also not true in the real case. Complex function theory is really, really special. All right. Moving along. Eventually. No. Where was I? Corollary 10.54 says, if you have a function which is analytic at z0, with power series expansion centered at z0, and if you have a power series for it, then the radius of convergence of the power series is the largest number r, such that f of z extends to be holomorphic on the disk. Let's see here. So there's two ideas at play there, right? Let me try to draw a picture rather than write that out. So the story that we're given is that you're given a function, right? Which is, say, holomorphic on this disk, right? Let's suppose this disk is D. So F is holomorphic on D, right? And then logically, you find F is equal to some k equals 0 to infinity of, a sub k, z minus z naught to the k, right? And this is got some kind of power series. This has some radius of convergence, right? This has radius of convergence r. The theory we've talked about today says that that radius has to be, well, it could be just the same size as, if D is a disk, which is all we talked about. I suppose the disk has radius, let's say little r for the sake of discussion here. So the red circle radius r. So then the question is it possible that the function could be complex differentiable on a larger, in other words, could it be holomorphic on a larger disk, right? Could there be a yet bigger circle on which we could extend? Could we, pick some R2 greater than R and find a holomorphic extension, right, of F? And the answer is no, you cannot do that, because if you did that, then that holomorphic extension would have a power series centered at z0, which would have a radius of convergence larger than the radius of convergence r, which is, of course, impossible. So finding the radius of convergence for the series which represents a holomorphic function gives us insight into what's the largest holomorphic extension relative to that center, which is possible. Now, if you start thinking about moving the center and thinking about choosing different centers and doing things other than disks, then the story is more complicated, but that's not for today. So not surprisingly, Sam has tried to ask me a question about 2 classes from now. Fortunately, I got enough sleep last night that I was aware of the question when it was asked. Didn't get sucked into it, as I sometimes will. Now, the rest of this section has beautiful formulas. Beautiful formulas for the exponential, the cosh, the sinh, the cosine, and the sine. I show you in the remainder of this section that we can define all of those functions. Well, I think what I do actually is I derive the power series representation of those functions for the complex domain, given the definition we already stated, right? But the truth of the matter is, philosophically, you could divorce yourself from anything we said up to this point about cosine, sine, cosh, and sinh, and you could just write down the series that I give in this section at the end of the section, and those would serve as definitions for these functions on the complex domain. That's probably really the better way to define functions is by series. Like, what is the exponential function? It's not a wrong thing to say, well, the exponential function is defined by this entire series. If you took this as the definition, if you take this as the definition of the exponential function, it's a straightforward but somewhat tedious exercise to show that e to the z times e to the w is e to the z plus w. Right? Actually, we'll get into the calculations which are needed to show that more in the next class, where I discuss calculation with series in the next class. We talk about dividing and multiplying series next class, all right? But you could prove that just using series calculation, all right? You could define cosine to be, the sum k equals 0 to infinity of minus 1 to the k, z to the 2k over 2k factorial. Right? You could define sine to be the derivative of that series, if you'd like, with a minus. Or you could write down the power series for sine and take that as the definition. Here's the really cool thing. If you define cosine to be this thing, right, we can actually find a completely ungeometric definition for pi. Think about cosine. What's it look like? What's the graph of the real cosine? Like that, right? So this is what? This is pi over 2. We know that. Here's a definition you could give for pi. Definition. 1/2 of the first real 0 for f of x equal to cosine x, where we're giving it the power series definition. One half of the first real 0 for f of x equals cosine x, like so, is pi. Oh, I should say twice, right? I can't do math. Twice. Right? Because if I want this is the 0. So x naught equal to pi over 2. So what do I got? I got pi is equal to 2x naught. If I want to give a definition for pi using cosine, I should say it's twice the first real 0 of cosine. You say, well, cosine was defined in terms of right triangle trigonometry. No, not anymore. This is the definition of cosine. There ain't no geometry there. That's just analysis and algebra. And so this gives you a way to prove things about pi to avoid any kind of circular logic, pun intended. Because there's no circle here, right? It's just an unending series. And this would be the sort of gateway to proving things like, I don't know, pi is transcendental. This gives you a careful definition of pi, which allows you to make things like that precise and rigorous. That's kind of neat, right? You're like, well, I don't want to teach high school math and tell students that, cosine, it's not adjacent over hypotenuse, right? It's the sum k equals 0 to infinity of minus 1 to the k over 2k factorial argument to the 2k power. That's what cosine is, right? I mean, no, there's a place where this should be said, and there's a place where this should not be said. This is the place where it should be said, right? But you should understand that there's more than one way to look at cosine. by the way, sorry to inject some A calculus in this, but the definitions I give for e to the z, cosine z, sine z, cosh z, and sinh z all still make sense over an arbitrary algebra. And all of your favorite trigonometric identities continue to still hold over arbitrary algebras. This has been proved. I proved this together with a student named Daniel Fries, who's now at Indiana. And I'm hoping to publish a paper which is sort of the result of that pretty soon, maybe this week. But anyway, thanks, guys. Oh, I should stop. Oh, I'll say more about that after the camera goes off.